Welcome everybody to the second day of the spectral geometry special session of the MCA 2021. Sorry. We recall you that besides these Zoom talks, the session includes 9 pre-recording talks collected at the forum where it is possible to interact via text. Also in the forum, you can find the recording of the talks on Zoom. So it is a great pleasure to introduce Carolyn Gordon from Dartmouth College that will talk about, do the Hodge spectra detect orbifold singularities?
Thank you very much for the invitation to this really wonderful session. This is joint work. Oh, no. Here it is. This is joint work with the people listed in order of the picture. So Magda Khalil, Liz Stanhope, Katie Gittins, Mary Sandoval, and Ingrid Membrio Solis. As you may have guessed, we were the spectral geometry team at a Women in Geometry workshop. So the motivating question is, orbifolds are a generalization of manifolds in which certain types of singularities are permitted. And so it's natural to ask whether compact Riemannian orbifolds with singularities are spectrally distinguishable from manifolds. The class of orbifolds includes manifolds, but it's larger. And the second question, we'll focus mainly on the first, is to what extent are the types of singularities encoded in the spectral data? And the spectral data for us will be the spectrum of the Hodge-Laplacian P-forms. In particular, when P is 0, then we're looking at the Laplace Beltrami operator. Most of the results in the literature have to do with the spectrum of the Laplace Beltrami operator. And so the new results will be about the higher P. So I'll first give a little bit of background on orbifolds, their heat invariance. Then we'll look at a partial history of results for the Laplace Beltrami operator. And then we'll look at the new results for the Hodge spectra. So what is an orbifold? Well, of course, manifolds are locally modeled on open sets in strictly Rn here. Orbifolds are locally homomorphic to open sets in Rn mod finite group action. The group actions can be trivial, so manifolds are orbifolds. Singularities correspond to points with non-trivial isotropy. And orbifolds are classified as good or bad. There's no judgment, but a good orbifold is one that is globally the quotient of a manifold by properly discontinuous discrete group action acting with only finite isotropy, and otherwise is bad. So for example, if you take hyperbolic space and quotient out by a discrete group that may have fixed points, you'll get an orbifold. Here's an example. This is what we call the PQ football. So it has two cone points. The neighborhood of the cone point is a disk in R2 mod rotation through angle 2 pi over P, the group generated by the rotation. The football is good if P equals Q, then it's just the quotient of a sphere by a group of rotations. Otherwise, it's bad. If we further quotient out the football by reflection through the plane passing through the two cone points, we get kind of a half football. It appears to have boundary, but it's actually closed as an orbifold. The red edges are not boundary edges, but they're part of the singular set because they're fixed points of a group action. They're called reflector edges. So this is a closed orbifold. And orbifolds are stratified spaces, smoothly stratified, so the strata are manifolds. The regular points form a single open dense stratum. I'm always assuming my orbifolds are connected. So single stratum of regular points, and then the singular strata are connected components of the set of singularities with a fixed isotropy type. So the half football, for example, has 5 strata. There's the one regular stratum. There's 2 reflector edges with C2 isotropy. Each of those is a stratum. And then there's 2 strata consisting of isolated points with dihedral isotropy. Now you can define Riemannian structures on orbifolds. In the case of a good orbifold, Riemannian metric just corresponds to gamma invariant metric on what we call a cover. We still say M is a cover of O, even though gamma can have fixed points. So it corresponds to an invariant metric on the cover. To define the Hodge-Laplacian forms on the orbifold just correspond to gamma invariant forms on M. The Hodge-Laplacian on M will take gamma invariant forms to gamma invariant forms, since gamma is acting isometrically, and therefore defines a well-defined operator, the Hodge-Laplacian, on forms on the orbifold. And for bad orbifolds, one works locally, things piece together compatibly, and everything works. And in any case, the spectrum of the orbifold for the Hodge-Laplacian behaves like that of a manifold. It's finite, each eigenvalue has finite multiplicity going off to infinity. Just a comment, we mentioned that if you have a codimension 1 singular stratum, it looks like boundary, but it's not. It's part of the orbifold singular set. However, if those are the only singularities, then the underlying structure does look like a manifold with boundary. And the orbifold Hodge spectrum does correspond to the Hodge spectrum of the Riemannian manifold with boundary if you impose absolute boundary conditions. In particular, the case of the Laplace-Beltrami operator if you impose Neumann boundary conditions. So let me say a little bit about heat invariance. So first, of course, in the manifold case, just to introduce our notation, we have the heat expansion where the various coefficients are spectral invariants. So this is for the Hodge-Laplacian of degree P on a manifold, and where, of course, n is the dimension of the manifold. A0 is a mole pole of the volume depending only on the dimension, and P. A1 is a mole pole of the total scalar curvature, again depending only on the dimension and on P. Here's the actual formula, and so on. And so these, of course, are spectral invariants. For an orbifold, Donnelly first computed the heat trace for Laplacian on good orbifolds, so quotient of a manifold by a discrete group action, first for the 0 spectrum and then for the higher spectra. He expressed the heat trace in terms of the contributions of each individual element of gamma, and each such element contributes a whole infinite series of terms. And then in 2008, Emily Dryden, Sarah Greenwald, David Webb, and I developed the heat trace using Donnelly's work in a very heavy way. The heat trace for the Laplace-Beltrami operator on all closed orbifolds, not necessarily good, and kind of collated the information so it's expressed in terms of contributions of each of the strata. And I wrote primary strata here. I haven't defined primary for you. But let me just say that most strata, singular strata, are primary in the sense that those of lowest codimension are always primary. If you have a primary that's not, if you have a stratum that's not primary, it's in the closure of at least 3 primary ones. So these are the ones that have a chance of showing up in the heat invariance. And there's only finitely many of those, so it's a little bit easier to deal with. And then in our new work, we did something similar for the Hodge Laplacians on P-forms. And in all these cases, the asymptotics are similar to the ones for manifolds, but you can have half powers of T here in the sum. And you're already familiar with this probably if you think about manifolds with boundary, where you pick up half powers from boundary terms. And here are the coefficients C sub j. P, of course, is just telling you which of the Hodge Laplacians you're looking at. So the C sub j's are given as follows. If looking at a whole power of T, so j is even, then so C sub 2j is the corresponding A sub j, exactly the formula you have for manifolds. So for example, C sub 2 is just the integral, a multiple of the integral of the scalar curvature. And then there's additional terms that can come from the strata of even codimension only. And the odd coefficients, the one that give you the half powers, only involve terms coming from strata of odd codimension. So in particular, it's easier to detect strata of odd codimension because they don't get mixed up with the other part of the invariance. And the lower the codimension of a stratum, the sooner it will appear in the heat expansion. Okay, so here's a partial history of results for the Laplace spectrometry operator. This is very partial. I'm only sort of giving things that have to do with can you hear types of singularities and things like that. So Emily Dryden and Alex Strohmeyer show that if you look at hyperbolic orientable closed two orbifolds, in other words, quotients of hyperbolic space, there's zero isospectral, those Laplace spectrometry isospectral, if with the same length spectrum, that's familiar for the manifold case, but also the same number of cone points of every order. So they are distinguishable from the hyperbolic manifolds. There's a series of papers, first by Liz Stanhope, then by Emily Proctor and Stanhope and Emily Proctor herself, and later by John Harvey, that get spectral bounds on orbifold isotropy type, and then diffeomorphism type, and then homeomorphism type under curvature assumptions on the orbifold. Ben Litowitz and Jeffrey Meyer recently got positive results for distinguishing certain non-positively curved, compact, locally symmetric spaces from ones that have singularities, assuming a number theory conjecture by Shanuel. So those are sort of sampling. Some applications of heat invariance to the question, could an orbifold with singularities be isospectral to a manifold? Well, as we mentioned, it's easier to see odd codimension singular strata. So the opposite parity theorem says not if the orbifold contains a primary singular stratum of odd codimension. If you want to allow strata, look at strata of even codimension, the results assume that you have a good orbifold, which kind of helps you distinguish, separate things out. So Craig Sutton showed that if you have a good orbifold, it can't be isospectral to a manifold if the orbifold and manifold have isospectral finite covers. In particular, if they have a common finite cover, they can't be isospectral. And you can allow infinite isometric covers if the cover is homogeneous. Each of these lets you get hold of the sort of A sub j part of the coefficients, so you can separate out the singular part of the coefficients. Okay, there's also negative results. Navi Bari, Liz Stanhope, and David Webb first showed that you can't hear the type of singularity meaning what the isotropic groups of the singularities are. And Juan Pablo Rossetti, Dorothée Schutt, and Martin Violent showed you can't hear the order of the isotropic groups. And there's many other examples of isospectral manifolds, not manifolds, mutually isospectral orbifolds, for example, by Emilio Lorette and others. But it's still open whether the Laplace spectrum distinguishes orbifolds of singularities from manifolds. So now let's turn to the Hodge spectra. And so the first question I want to ask, since the Laplace spectrum alone is not known to be enough to distinguish orbifolds from manifolds, it's still open question. How about if you take two spectra, the 0 spectrum and the 1 spectrum, together, are they enough to distinguish orbifolds with singularities from manifolds? And we were able to answer it if the singular set is big enough. If the singular set of the orbifold has codimension at most 3, it's distinguishable from a manifold. And so in particular, orbifolds and manifolds in dimension less or equal 3 are always spectrally distinguishable by their 0 and 1 spectra together. So next, let's consider a single P spectrum. And what can we say for P greater than 0? The one result I'm aware of historically is a negative result by Juan Pablo Rossetti, myself, if n is even and P is half the dimension. In general, the middle degree Hodge spectrum contains less information than other spectra because of Hodge duality, or Poincare duality, which, yeah. To consider other P, I need to first introduce some polynomials. These are the Crouchik polynomials. So n here is any positive integer, and P is an integer between 0 and n. So n is going to correspond to a dimension of our orbifolds. P is the Hodge P. And there's these combinatorial polynomials. The formula isn't particularly important for us. But these are studied widely in the combinatorial literature, and they first appeared in the spectral literature in work of Roberto Mioteo and Juan Pablo Rossetti, who expressed multiplicities of the eigenvalues in the Hodge spectrum of Bieberbach manifolds in terms of these polynomials, and used them to construct isospectral Bieberbach manifolds. When P is 0, the polynomial is identically 1. For other values of P, there may or may not be zeros. The zeros are widely studied in the literature. And we're going to get both negative and positive results using these polynomials. So let me let script orb superscript n of L denote all closed n-dimensional orbifolds whose singular set has codimension L. And we want to ask, are orbifolds in here distinguishable from manifolds? And the answer, if n is greater or equal to 2, and if you take any P for which the P's Crouchik polynomial of degree n vanishes at L, then the answer is no, there's a flat orbifold with singular set of codimension L and a Bieberbach manifold, so a smooth manifold that are P isospectral. On the other hand, if L is odd and the Crouchik polynomial of order P at L doesn't vanish, then the Laplacian the P Laplacian actually determines the volume of the singular set for all orbifolds with singular set of codimension L. And so in particular, it distinguishes orbifolds in here from manifolds. This first result is actually new even for p equals 0. And for p equals 0, remember the Crouchik polynomial never vanishes. So it says that the Laplace-Beltrami operator determines the volume of the singular set whenever the singular set has odd codimension. So in summary, does the spectrum distinguish orbifolds with singularities of codimension L from manifolds? Yes, if L is odd and the Crouchik polynomial doesn't vanish. No, if Crouchik polynomial vanishes. Still open if L is even and the Crouchik polynomial doesn't vanish. Let's see how we're doing on time. Let me skip a couple of things since I think I'm about out of time. So let me just go on to kind of a fun example to end with. This is going to be the middle degree Hodge spectrum, so not so surprising, but I think it's kind of a fun example. There's a flat 3-pillow with 3 cone points. So what I mean by a pillow, kind of looks like a pillow. The underlying space is a sphere. It has 3 cone points. So it's just made by taking, in this case, 2 45, 45, 90 triangles, sewing them together. And you can stuff it, but you have a flat orbifold and a square. And the one spectrum of this orbifold equals the one spectrum of the square, where on the square you can put absolute boundary conditions. You can view it as a manifold with absolute boundary conditions, or you can view it as an orbifold where you have 4 reflector edges and 4 the corners or dihedral points, either way. So I'll stop there. So thank you.
Thank you, Carolyn. Very nice talk. Are there any questions?
I have a silly question. So this is something about complexity, I guess, not necessarily for orbifolds, but so assume you look at somehow very nice metrics, I don't know, real analytic or something, and and in practice, you probably know the first, 100,000 eigenvalues, right? Not all the way to infinity. So it's interesting how, if you know more and more eigenvalues, how much more you can pin down the metric. So the question is fairly vague, but sort of how much more information you have once you get more eigenvalues, right?
Yeah.
So of course you can ask about spectrum and differential forms as well. Yeah, I don't know. It's not very well defined. But.
Yeah, that's an interesting question. Yeah. I mean, I've seen papers many years ago about, I think, approximating the volume, how many eigenvalues you need to get a good approximation of the volume, but I don't remember the results. But
I guess something like in 1D Laplace plus potential, maybe you can get a lot of information, but so that's probably well understood. But I don't know. I haven't thought too much. I'm just asking.
Yeah. Yeah, I forgot his last name, Jeff. I forgot his last name. That's terrible. This has been so many years ago that I think was approximating volume, but that's the only one I remember.
I see.
Yeah.
Thank you. I'll try to look.
I might be able to find it, if so I'll send it to you.
Okay, are there any other questions? I have one question. There are some numerical evidence saying that on the round sphere quotient by cyclic groups, which are length spaces when the action is free, there cannot be any p-isospectrality between a, let's say, orbiform length space and a real length space. Is it? Does your approach can say something about this?
Let's see. What dimension? You're in dimension 3 or?
Any dimension.
Oh,
Any
an
dimension.
I see.
I mean, the heat invariance can say something with this orbifold that have constant sectional curvature.
Oh, well, actually, yeah, an orbifold and a manifold. Oh, for the zero spectrum, we know an orbifold and a manifold for common cover can't
Yes,
be.
but for p greater than 0.
Okay. Let's see. So if the dimension, so we're just talking about, let's see, the codimension of the singular points is the dimension of the, is that right? They're all,
I'm
wait a
not
minute.
sure.
Oh, what's the codimensions of the singular strata? Wait, if the singular set has odd codimension, then the Crouched polynomials will tell us the answer. But if it's even, then I wouldn't know. Yeah.
I can check it later. Okay.
Yeah.
Okay. Let's say thanks again, Carolyn.
There's this movie